Hi ladies and gentlemen, here's another video on the language of propositional logic. This time I'll talk a little bit more about the syntax of the language of propositional logic. In particular, I'll talk about 5 different complex well-formed formulas, what it means for a formula to be a literal negation of another, and 3 conventions for simplifying the presentation of well-formed formulas. So first off, in an earlier video, I talked about a distinction between an atomic well-formed formula and a complex well-formed formula. This distinction was that an atomic well-formed formula is a single propositional letter, whereas a complex well-formed formula is any well-formed formula with at least one truth functional operator. Now, these complex well-formed formulas can be further classified according to their main operator, that is, the operator with the most scope. And so, a well-formed formula with a negation as the main operator is a negated wolf. A well-formed formula where the caret, or the sign for and, or the operator for and, is the main operator is known as a conjunction. Where the v, or operator for or, is the main operator is a disjunction. Where the right arrow is the main operator is a conditional. Where the double arrow is the main operator is a biconditional. Now, some of the components or subformula of these 5 different complex well-formed formulas have their own names. The conjunction, where the and is the main operator, is composed of 2 conjuncts, P and R. The 2 sides of the conjunction are known as conjuncts. The disjunction has 2 parts, and those 2 parts are known as the disjuncts of the disjunction. Now, the conditional is a little bit different. In the subformula to the left of the right arrow is known as the antecedent of the conditional, whereas the formula to the right of the right arrow is known as the consequent of the conditional. Next, I want to turn to a discussion of what it means for a formula to be a literal negation of another formula. Now, one way of thinking about this is to say, well, how do I take a formula and form its literal negation? And the way you do this is to simply put parentheses around the formula in question and add a negation to it. If you remember the formation rules, which I talked about in an earlier video, the way you'd form a literal negation of a formula is to apply formation rule 2, which forms a negation of a formula. It's important to note that when we are talking about the literal negation of a formula or a proposition, we're talking about the negation of the entire formula and not just some smaller subformula of it, some part of that formula. So let's look at a couple of examples of how we form the literal negation of certain formulas. So if we take the formulas on the left-hand side as our example, and the right-hand side will be the negations of those formulas. In the first example, we have P, and to form the literal negation of it, we simply put parentheses around it and add a negation. In the case of 2 here, we have a P right arrow R, and we could put an additional set of parentheses on there and then add a negation, but for all intents and purposes, here we can simply write the negation because there's no ambiguity as to how that negation is operating. It's negating the whole formula rather than just part of it, that is, rather than just P or just R. Likewise, in the third example, we have not P and R. We want to make sure we negate the entire formula and not just the not P or not just the R. And so we can put a negation on the outside, and it's clear that the scope of this leftmost negation is applying to the whole formula. So I want to talk now about 3 conventions concerning parentheses. So these conventions are introduced, and they're not necessary, but they're introduced to make the formulas a little bit easier to read. The first convention involves removing a set of parentheses if the scope of the negation operator is a single propositional letter or is just a negated propositional letter. So here are a couple of examples. On the left-hand side, you see not, and then there's these open parentheses, P, close P. But the convention says, well, if the negation is just ranging over a single propositional letter, it's not any kind of confusion as to what it's applying to. It's just applying to that P, so we can drop out the parentheses. In the second example, or the second row, you see the same thing. It's not open parentheses, P, close parentheses. We don't have any confusion of what that negation might be negating. Is it negating a larger subformula or a smaller subformula? We know it's just negating P. Similarly, at line 3 or row 3, we have a set of negations and a set of parentheses. What we see this formula as saying is not P, and there's not any confusion about what that outermost negation, the leftmost negation, is negating. So we're going to simply drop out all the parentheses because there won't be any confusion about the scope of those operators. The rightmost negation is applying to the P, and the leftmost negation is applying to the not P. Second convention involves when we are looking at formulas with lots and lots of parentheses, we might want to make use of different scope operators or scope symbols or characters to kind of more clearly offset the scope of different operators. So we can introduce square brackets and curly braces if we don't want to make use of lots and lots of parentheses, instead want to make use of different types of parentheses to kind of clearly see what the scope of different operators. So let's take a look at two examples. So in the first row, you see there's on the right hand side, you see there's a lot of parentheses, and it might be kind of confusing. And so you might say, well, to make this easier to read, I'm going to drop out one set of those parentheses and add square brackets for their in their place. In the second row, we see a formula with a number of parentheses. One way to more clearly see this is to swap out certain parentheses with either square brackets or curly braces to make the formula more legible and to make the scope of the various operators easier to identify. A third convention is employed when a set of parentheses doesn't serve to disambiguate the scope of an operator. This occurs most often when an open and closed parentheses has another and open and closed parentheses within it without anything else. So for example, in the case of not open parentheses, P, right arrow Q, close parentheses, you see that the outermost set of parentheses has immediately within it another set of parentheses. And so it's easier to see the formula, and there's no confusion about the scope of the operators if we drop one of those set of parentheses out. Alright, ladies and gentlemen, this has been another video on the language of propositional logic. Like the video if you thought it was helpful, and subscribe if you're interested in seeing more videos on topics in logic.